Good afternoon, everybody, and welcome to the European Marine Board's third Thursday Science webinar series, coming to you at a different time. Usually we are at 1 o'clock, but today we are at 3 o'clock, so nice to see you all. That's right. So just some housekeeping rules. Please make sure that your name is clearly entered so that I can know who the question is from. If you want to ask a question, please use the Q&A and let us know where you're from, which country, which organization, so that we know who we're speaking to. If you have any technical problems, please use the chat function, and be aware that this webinar is being recorded and live streamed on YouTube, so act accordingly. So thank you again for all that are here. Today our webinar is linked to our Future Science brief on addressing underwater noise in Europe, which came out 2 years ago now, maybe even 3 years ago, 2.5 years ago now. And the title of the talk is Implementing Ocean Sound as an Essential Ocean Variable for the Global Ocean Observing System. And our speaker today is Peter Tyack. He is a professor of marine mammal biology at the University of St. Andrews and an emeritus research scholar at Woods Hole in the US, hence the difference in time of our talk. So without further ado, I'm going to stop sharing my screen now and stop sharing. There we go. And Peter, maybe you can do that. There we go. Perfect.
Yes, thank you so much, Sheila. I'll share my screen and just ask if everybody can see this screen clearly now.
Yeah, we can see it. It's not in full screen mode yet.
Now it should be shown as a full screen.
Yeah.
Great. Thank you so much. So yes, I will be talking about implementing ocean sound as an essential ocean variable for the global ocean observing system. And I thought for starters, if any of you are unfamiliar, I thought I'd start with a brief description of the global ocean observing system. At the beginning of this project, I was not as familiar as I should have been. The start of this was the recognition that the global oceans are critical components of climate change, both in terms of flux of temperature and of carbon dioxide. And the Global Ocean Observing System was first established in 1991 by the UN Intergovernmental Oceanographic Commission to support climate science, so quite focused on climate as the observational backbone for operational forecast systems. And I'm a research scientist. I mainly focus on the red circle areas of the increasing readiness levels. The Global Ocean Observing System views a major part of its role as developing quite mature elements of the observing system. And you might think about, for example, weather. The underlying measurements required for your weather forecasts are part of quite a complex system that started with initial research ideas, developed into developing networks for local and regional observation, finally creating the kind of system we have now, where we have global measurements and several global models, allowing users to be able to predict short-term weather change. So while my world is usually in the sort of peer-reviewed innovative science idea, the involvement in groups requires focusing on developing a much more mature system. And the framework for setting this up starts with societal issues like responding and managing climate, predicting and managing climate change. And the point about these essential ocean variables is when you start with a societal issue, the essential ocean variables are the decision of what needs to be measured in order to address the issues. I am not, let's see if, there we go. Once you had developed the issue of essential ocean variables, make a decision about it, then the question is how to measure it. What sensors do you need to use? And what are the scales in the global ocean over which you need to make the measurement? Once you think about sensors and scales, you need to get practical about how do you make the observations? What platforms do you use? What facilities are required, and how should they be maintained? Again, think about the weather system. There's an enormous infrastructure for this. This is also needed for ocean observation. And as you collect the data, you need to worry about the data infrastructure and assembly centers. A key element about the global ocean observation system is the data should be freely accessible globally to anybody in as close to real time as possible. And this is a challenging data management requirement. Once the data is available, the issue is to develop information products and services that are useful to guide decisions about those societal issues. And the idea is that there's a cycle here that you identify gaps in the information required to make the right decisions, and that may lead to additions for essential ocean variables. And ocean sound is actually a latish addition, which comes in part from a recognition of gaps. If we think about the societal issues that Goose is, oh, let me also mention, if people have questions, like about the structure of anything that I'm describing, please send a chat. And if Sheila thinks that's important to clarify while we're going, I'm very happy to stop and answer the question. The societal issues that Goose initially focused, yes, go ahead.
I'm just going to interrupt you. Send it in the Q&A. Don't send a chat.
Oh, I'm sorry, Q&A.
Okay.
Yes. The Goose initially focused on climate issues and forecasts and warnings, like we would think about for weather forecasting. And it has recently broadened to assess marine biodiversity and the status of marine ecosystems using societally and scientifically relevant biological essential ocean variables. So ocean health has been added and creates a broader scope for the observation system. Just to give you an idea about the coverage, here's an example of all of the platforms that Goose had deployed for making ocean observations in May 2021. And you can see it's a remarkable coverage of the world's oceans. So in general, for measuring some of the parameters, we have platforms all over the world. And this comes through collaborations between individual research organizations, nations, and regional organizations as well, leading to remarkable coverage. How about the decision about what you need to measure for this kind of large-scale system? Goose has expert panels in 3 areas linked to those societal issues: in ocean physics and climate, biogeochemistry, and biology and ecosystems. Each one of these panels identifies the essential ocean variables in their area. Depending on the impact, the variable has to address these issues and also contributes to understanding from a scientific perspective, or the application of them from the issue of a service for the societal issues. And it has to be technically, politically, and economically feasible to make the observations. So here's a list. I don't mean for you to have to read the whole thing here of all the lists, but I'll just mention the physics and climate essential ocean variables are mainly physical oceanographic measurements. Biogeochemistry are more flow of chemical compounds through the oceans, which, for example, is really important in thinking about carbon flux in the ocean and stability of its being sequestered. The biology and ecosystem essential ocean variables are all focused on specific taxons in the ocean of marine organisms, less focused on broader ecosystem and more focused on estimating the distribution and abundance of specific taxa. There are 3 cross-disciplinary essential ocean variables: ocean color, most of which comes from satellites; marine debris, which is policy related; and ocean sound. And the key about ocean sound is that it provides information for all of the essential ocean variables marked in orange. So there's some physical ones and quite a few biological ones for which sound provides information. And the ability to predict how sound propagates is influenced by all of the essential ocean variables marked in green: sea surface temperature, subsurface temperature, salinity. These affect how sound propagates in the ocean. Here's an example of just to see the coverage of the biology and ecology metadata. And as you can see, if you look in the upper left, the variables are all focused just on taxonomic groups. And while there is pretty good coverage, it doesn't match the May 2021 scope of all of the physical measurements that I showed. In particular, we're missing Arctic, Antarctic, and pelagic data from pelagic regions. But still, you can get a sense of the scale of effort to combine observations about the distribution and abundance of marine organisms here. So now, what about this interdisciplinary, cross-disciplinary measure, this ocean sound essential ocean variable? It was developed by a self-organizing group called the International Quiet Ocean Experiment. We had a working group which was funded by the Partnership for Observation of the Global Ocean. And the POGO link led us to realize that even though sound is the medium through which information propagates furthest in the ocean, so it means it's the way to sample over the biggest ranges, there was no essential ocean variable for sound, like there was for ocean color. The measurements are purely physical. They're sound pressure or particle motion, the displacement, velocity, or acceleration of particles in the medium. The platforms and systems overlap with all of the other ones. There are cabled systems, moored stationary systems, autonomous drifting and towed platforms that carry acoustic sensors, and even animal tags. Tags on animals can measure sound. The goal of this group was initially to look at the societal drivers and pressures from the goose perspective, and the majority of drivers and pressures are addressed by sound. Another issue this group had to start looking at quickly was standardization and archiving of data, and how to lead an implementation plan for the ocean sound as an essential ocean variable. If you're interested, the first action we did was to develop a specification sheet for the ocean sound EOV. That was last updated in 2018. It's rather old, but you can access it using the link I have below here. Just to briefly go through the process of establishing the EOV, we started in August of 2015. We didn't finish until about 2020, but the approval of the ocean sound essential ocean variable came through in August of 2018. This was by the Goose Biology Ecology Panel. So a 3-year process to develop the ocean sound essential ocean variable, and then a couple of years to set up to be able to develop ways to implement it. And the implementation plan, which forms the core of what I'm discussing, was developed by an implementation committee that was formed in 2021 at the end of the timeline that I showed you before. It took about 3 years to start drafting the plan, to release it, to revise it, and for final release. We took input from the global ocean acoustics and bioacoustics communities. These are very stovepiped groups in terms of discipline. So there are engineers and physical acousticians who model how sound propagates in the ocean. There are biologists interested in how animals make and use sound. There are conservation and environmental scientists interested in the effects of noise on ecosystems. They didn't tend to talk to each other, and this process was extremely helpful for bringing all of these communities together. And the committee, just to point out, again, I don't expect you to read it, but it was quite diverse from an international perspective, and this was also very important for us to develop a global view. So what about using sound to measure ocean variables? Ocean acoustics is in general split into 2 fields: active acoustics, which involves producing sound, like a depth sounder or a sonar, and then listening for the echoes, and passive acoustic monitoring, which involves listening to other things that make sound in the ocean. In terms of the biological parameters that can be measured, and in orange are the actual essential ocean variables, you can measure sounds that invertebrates, fish, and marine mammals, or plankton and fish make. You can also measure backscatter. The standard way to measure the distribution and abundance of plankton and fish is using active echo sounders and measuring the echo strength that comes back from them in the ocean. In terms of physical parameters, I mentioned depth sounder on the left, sea surface height, temperature, currents, and sea ice can be measured by active acoustics. For some reason, bathymetry, the depth sound application, is not listed in the EOVs. For the on the right side, for passive acoustic monitoring, waves, wind, sea, ice, earthquakes, tsunamis, and rain make noise. And just to be really clear, the ocean sound essential ocean variable only involves passive acoustic monitoring. It's monitoring in the ocean for sounds produced by things in the ocean. And that it also includes human activities which are not part of the global ocean observing system, but we view as quite important to think of in terms of stressors, and they may be dominant sources of noise in some frequency ranges in the ocean. The outline of the ocean sound EOV implementation plan is listed here. I will just point out, I've just discussed a lot of the societal drivers that are mentioned in the introduction. I will then focus a bit here on measurements and derived data products to meet our goals, but I will do that close to the end because I want to start by talking about how we tailor acoustic observation systems for different uses and give you a sense of some of the actual applications for which ocean sound is so important. So in the broadest scale, if we think of the goose goals of climate change, the relevant parameters are wind, waves, rain, sea ice. For ocean health, measuring the status of marine ecosystems, loss of biodiversity, distribution of species, and impacts of sound on wildlife. And for monitoring threats, sounds of earthquakes and tsunamis, that can be monitored by sound, and this is a very important element for tsunami warning. And naval activities and nuclear explosions are monitored globally using sound. For the climate change applications, we're interested in very large spatial and time scales, centuries and globally. For ocean health, it's sort of ecosystem based. It's typically days to a decade over a couple kilometers. And for monitoring threats, you typically want real-time feedback. So the time scale is quite small, say less than a day, but the spatial scale can go from meters to global. And the different ways we can measure, deploy sensors to meet these scales are on the right. So cabled observatories are the best way to measure decadal or longer time periods with a stable system. Fixed autonomous systems like buoys that are moored on the seafloor are in between. And then animal tags and mobile autonomous systems are better for the shorter time and spatial scales. So these are the kind of deployment methods. I won't go into much more detail about them, but because it's technically quite well understood now. I will mention, again, from the goose perspective, the maturity of systems is very important. And the Comprehensive Test Ban Treaty Organization, since the early 2000s, has had 11 very well calibrated acoustic sensors that continuously monitor the global oceans for nuclear explosions for decades. And this is because sound propagates so well in the ocean. This is one of the few modes of monitoring where 11 sensors are sufficient to measure, to detect a nuclear explosion that occurs anywhere in the world's oceans. Most other methods require sensors that are either move through the ocean or much denser distribution. So this is a very important element of sound in the ocean. The International Quiet Ocean experiment, as part of organizing for the Ocean Sound EOV, has been maintaining a meta database of underwater sound observations. So people who make recordings have reported to the database. It's available on the website you see on the lower left. We now have up to 5,000 records in the current period. And if you look at the locations, they're not quite as good as all of the May 2021 distribution, but they're pretty good for a global distribution. And they have some of the same problems the biology ones had of pelagic oceans, Arctic and Antarctic coverage needs to be improved. The striking thing here is the growth in deployments. So the deployments are typically project specific. They're not put in place in order to help a global observation system. But the accelerating pace of deployments means that we're likely to have an enormous set of data, and we'll just need to have a gap analysis to focus on the areas where the natural expansion of this set of observations isn't sufficient to cover what we need for the global observation system. To give an example of some of the benefits of decadal plus time series, I mentioned the CTBTO, these calibrated hydrophone array. On the left are the locations of the 11 sensors. The white ones are hydrophones. The bottom ones are measure acceleration on the sea floor. And data from Wake Island, which is on the right of the world map, HA11, is presented on the right side of this figure, and it shows an increasing uh, annual fluctuation in the intensity of sound pressure measurements in a low frequency band over the period from 2008 to 2020. So something interesting is going on in this site that's leading to significant annual changes in the sound pressure. But just by looking at this, we can't know what are the causes of it. Stephen Robinson's group in the UK has done a really interesting analysis trying to predict these changes in sound levels from these sites. And what they did was here you can see a figure. The blue dots mark the measurements and the predictions of the noise levels from January 2018 through the end of 2020. The red dots on the right of the figure show the start of COVID. And in January 2020, the dots pretty much fit the expected levels based upon the previous data. However, during COVID, the levels were quite a bit lower. So between January 2020 and July 2020, you should see all of the red points are below the estimate of the blue line. And this is interpreted as COVID quieting, as the reductions in human seagoing activities caused by COVID actually led to a measurable decrease in the level of deep ocean noise at this site at Wake Island. And this was true for most of the sites that were analyzed. So we can detect global changes in ocean noise because of the COVID pandemic. Again, though, in order to interpret what these changes mean, it's absolutely essential to sort out what the sources of those noise were. And the word ocean soundscape or soundscape means the characterization of environmental sounds in terms of the spatial, temporal, and frequency attributes, and using that information in order to infer the different types of sources that contribute to the sound field. So the way to understand a soundscape, we need to be able to attribute what are the reasons that the levels are what they are in certain places and times within different frequency bands. And the drivers are oceanic processes, geological tectonics, climate, and policy changes. Those affect biological sources like fishes and whales. They affect anthropogenic sources like sonar, shipping, and seismic air guns. And they affect geophysical processes like earthquake, winds, and ice. And those lead to these different components on the top that you can measure in ocean sound. Since World War II, underwater acousticians have known that human sources can dominate the average deep ocean ambient noise in certain frequency bands. So in the frequency band of about 10 to 100 hertz, human shipping, commercial ships in the last century have dominated the noise. There was a window in the pre-industrial ocean, right where low-frequency whales communicate, that now is dominated by shipping noise. And if you look at the frequency range from about 200 hertz to about 20,000 hertz, wind speed dominates. So wind speed in knots, as that increases, and as the sea state increases, the ambient noise in that frequency range increases. That's been known for a long time, but we can now are thinking about inverting that process. So acoustic ocean engineers wanted to know how heavy the shipping was or what the wind speed would be, what that impact would be on the noise floor, so they could predict how their systems would operate, how effective they'd be. But if you look on the right, you can see wind changes in an area of an acoustic recorder on the top, sea surface temperature measured at that site, ice coverage measured near that site, and the median of the noise in a frequency band on the bottom. And if you look at the bottom, the peaks of ocean noise correspond to the lowest levels of ice coverage. High levels of ice coverage may reduce the waves from wind and may reduce the impact of noise. If you look at sea surface temperature and wind, you can see that during the summer, when the sea surface was warmest, the wind was the highest, and that also correlates with the high noise floors. So how do you sort out? Is this because of an environmental change with ice coverage? How much is due to the wind? And a key for that is being able to dive into long-term data sets and look at short-term to see what the sources of sound are. And I'd like to credit the Alfred Wegener Institute as a wonderful example of an academic institution that has provided a very significant contribution to the ocean sound essential ocean variable by developing the open portal to underwater soundscapes, which is very important for ocean sound data management. You can see the map. It isn't fully filled out. It's still just in its infancy. But I'll show us an example of data from a sanctuary provided by the US, a National Oceanic and Atmospheric Administration near Cape Cod in the US. And here's an example of an annual spectrogram of their data, which shows some event happening in the end of October, early November, but very hard to interpret. If we zoom into a monthly spectrogram, we can see lots of events that are hard to interpret too. I think I should point out here where the frequency of the sound is on the y-axis. So this would be like a musical scale where the high frequencies are up high and the low frequencies are low, and time by day is indicated on the x-axis. Here again, it's hard to sort out what's going on. If you zoom all the way into a daily spectrogram, you can see the three very dominant noise sources here during this day were ship passages. People who are used to looking at this can easily detect that those are ships. And there are, if you zoom in even more, you can see some sources of sound from whale calls, from other sources as well. But the dominant sources are ships, which would allow you to then back out what were the sources for the soundscape in this frequency range at this time. And so this kind of tool is essential and very helpful coming online now for our community. People who've done this kind of analysis can point out for long-term soundscapes, they can look at over, say, a year, how do the sound levels, the amount of energy at different frequency ranges, now frequencies on the x-axis, vary over time. So that the loudness, the amount of energy in different frequency bands is indicated on the y-axis for different frequencies on the x-axis. And by looking at it carefully, they were able to show that the area in the magenta box is dominated by blue and fin whales. The area in the black box is dominated by shipping, and the part in the blue-green box is dominated by fish. So here we can start to get the soundscape and identify what are the statistics of variation in energy over time and what are the sources that are causing those. Comparison of different sites like Fram Strait in the Arctic, Ascension Island in the tropics, and Bransfield Strait in the Antarctic shows with these kinds of plots of amount of sound energy as a function of frequency, show that Ascension Island is significantly higher average noise levels than either of the polar regions. And zooming in has shown that that's primarily from sound from air guns used for seismic survey. So that shows that this is a place, Ascension Island is a place where there are elevated levels of a potential stressor, if noise is a stressor for marine life compared to these other sites. So we can get a spatial view of variation in sound as a stressor, but it's very important then to try to get an estimate of what is the likelihood effect of the sound on wildlife. And passive acoustic monitoring over the past 2 decades has been beautifully developed to be able to monitor the effects of sound on wildlife. Tagging of a toothed whale called a beaked whale has shown that they make deep dives for thousands of meters over hours at a time, where they use echolocation clicks to forage. These echolocation clicks can be mapped, and on the lower left, you can see the red dots show the location of underwater hydrophones, underwater acoustic sensors in tongue of the ocean in the Bahamas. And the color map shows the density of echolocation clicks produced by the foraging animals, the percentage of time in which they're detected foraging at depth before a sonar exercise. The middle panel shows the whole area goes dark during a sonar exercise. The animals have completely silenced, they've completely stopped foraging, and tag data shows that many of them have moved out of the entire area. And about 3 days after the sonar exercise stops on the right, you can see the density of animals foraging starts coming in. Dave Moretti's group at the Naval Undersea Warfare Center in Newport, Rhode Island, has used these kinds of data to estimate the received level of sonar sound at hydrophones during exercise, actual naval sonar exercises that detected whales clicking. And on the left figure, the little tick marks on the upper right show animals detected clicking, and no detection is on the bottom. And these data then can be converted on the right side into a dose response function that shows the probability of these animals being disturbed in their foraging as a function of the received level of the sonar sound. And if you couple the mapping of noise that I've shown in the previous slides with this kind of dose response function, you can actually evaluate what the impact of sound is likely to be on these animals, and even integrate it over time in terms of the energetics of their foraging. As a last function use of these sounds, I'll point out that passive acoustic monitoring can be used to estimate the density and abundance of vocalizing animals. Your estimate of the density equals the number of cues, like the clicks you detected in a unit of time, divided by the probability of detecting the cue within an area A, and where R is the call rate to convert the number of cues to the individuals. And the method requires detecting calls from various stations, estimating the probability of detecting calls as a function of range, and measuring the call rates of different individuals. But this is a very useful way to be able to estimate the density of animals. It's persistent. It allows you to look over decadal scales. You can use long-range detection for low-frequency sounds, and that can even discover unknown aggregations, for example, of spawning areas for fish or calling whales. And the biases are different from other methods like visual sensing, but not many calls can be identified to species, and some species don't call at all. So it's best viewed as a targeted complement to other methods like visual sighting and eDNA for estimating biodiversity. It's not a panacea in its own right. And I'd like to then now just close by talking about how we structure measuring ocean sound, the essential ocean variable, going from the primary physical acoustic variables to the primary goose goals. I'm afraid it's rather complicated. It requires calibration of the methods, data management, sound propagation modeling, understanding the characteristics of sound sources. And in the end, what you end up with is a significant set of, you need to measure both the acoustic parameters, supporting variables on propagation and sound sources. You need good data management, sound propagation modeling, and the derived data products are changes in sound level over time, soundscapes, and detecting transient events caused by particular sources. And together, these allow you to address the goose primary goals. In order to take advantage of the kind of applications I've described, we still need to build capacity to improve access globally to ocean acoustic recording equipment. Standards for calibration are superb, but there's a need for cheap access to calibration facilities globally. There are excellent standards for analyzing noise data. Those are really in place now. Ocean acoustics does generate giant data sets, and the data may increase in value with age. So we have a significant need for cheap, sustainable, long-term archives set up for open international access. Some nations have these in place for military purposes, but the key here is we need open international access. For governance and funding, the implementation plan focuses on some of the essential requirements. We need a coordination function for the growing bottom-up international network of ocean acoustic sensors. We need a QA/QC function for the ocean acoustic data, and supporting variables, and to coordinate and ensure long-term sustainability of acoustic data records and these derived data products. There are some superb, strong national efforts, and the example I gave from Avi before. And we also need to focus on global capacity building and technology transfer. The methods for both measuring underwater sound and recording it are dropping drastically in cost and size because of electronic miniaturization. And just to close, here is how you can access the Ocean Sound Essential Ocean Variable Implementation Plan. And I'd be happy to accept questions or open discussion.
Thank you. Thank you very much, Peter. That was great. Just a reminder, people, that you can put your questions in the Q&A. There has been two. One is, will the presentation be made available? Yes, indeed. It's, as we said, it's live streamed on YouTube, so you can always watch it there again. But these slides will also be, as I understand, will be in PDF form on our website. So you'll definitely be able to get them there later.
Yes, and I gave a location for the website for accessing both the specification sheet and the implementation plan.
Yeah. So you'll definitely be able to find that again. Great talk. Manfred, if I see somebody raise their hand, you can't speak, but please type your question into the Q&A, and I'm happy to read it out. So Peter, I guess my first question to you is, what's next? What do you think is the thing that we need to do next to make sure that this happens?
Yes, I think in terms of the human efforts, we have working groups in all of those areas I mentioned that need to be attacked for governance and funding. But the way the global ocean observing system, it's organized from an executive group in the UNESCO building where the IOC is headquartered in Paris. But it depends completely on academic institutions, nations, and regions such as the EU in order to actually implement setting up the networks and coordinating their activities. So the map that I showed of the May 2021 global coverage of the oceans, most of the global coverage came from floats called Argo floats. And the US and France stood up to organize coordinating an effort where each oceanographic institution globally often buys and sets up or builds these kinds of floats and puts them in their own waters. But it's organized with these two offices to be able to coordinate the efforts. That's what we need. We need to have organizations doing the kind of thing that Avi did with the data management for their Opus system, to actually commit resources to set up a framework, to set up a plan that can ingest data, or in the case of, say, the hydrophone deployments, we really need a coordination office. We need some support for about one person in order to be able to do that. That's small scale in terms of the global efforts, but our community is really focused on our own individual projects and deploying them. And we're the ocean acoustics community from all of the different disciplines is very excited and motivated to do this. But it requires institutional support, and that's the area I think that we need the most focus, particularly for long-term support. We have large data sets. They need to be quality controlled and put in place so that somebody 20 years from now can say, is the North Sea more stressful for the animals that live there or less stressful?
Yeah. I see we have two questions in the Q&A, and then Paula, who is one of my colleagues and can't ask in the Q&A because she's on our system, has also got one. So let's go through those quickly. Aristides, whose last name is very long, Prospathopoulos asks how AI developments are expected to affect passive acoustic monitoring efforts at a global scale. And I would add to that, I would imagine AI would really help with actually analyzing these huge amounts of data sets. So do you have any idea on that?
Yes, I do. The weakness for AI in our current situation is our data sets aren't big enough. We have fields in which our culture has been a graduate student looks over gigabytes of data and comes to conclusions. And I think that this is a very interesting and important question. We haven't been set up to actually be able to analyze the data sets of the scale that we're collecting globally. And I think that as AI provides the opportunity for researchers to ingest these giant data sets for their own analyses, I think that will become an extremely strong science driver for the coordination efforts that are required to integrate the databases across all of these national and regional efforts. And I can comment in my own area is marine bioacoustics, and many marine animals make variable and complex sounds. The issue of sorting them out to species is quite complicated. And as sounds propagate through the ocean, they change quite a bit in ways that we know how to predict, but haven't really been able to pull together in a way to do this. I think that AI will be an incredibly powerful tool in our efforts to use sound to establish the distribution and abundance of marine organisms in a way that we just haven't even thought of yet.
Yeah, and I will say that my understanding is at least in the active acoustic world. So when they ping to figure out how big a school of fish is, which to me that's active acoustics, right?
Yes.
In that field, I think there's a little bit of work that's done already by the stock assessment people. So I imagine there's some there's some learning that can happen there.
Absolutely.
Yeah. Okay, and then the second question is by Isabel Avila, who asks, the sound data of this global database are recorded with the same system. Is it? Or does it come from different acoustic sources? And if it does, is there some sort of standardization, which I would imagine would be very important?
Yes. Given the time constraints, I didn't go into all of the detail. Again, in the last 5 to 10 years, there has been a major effort in our community to develop standards. So there's a set of ISO standards for underwater sound measurement and for how to measure calibrated measurements of the different sound sources like ships. And the ISO standards are available. There also is software available. There's one called Manta that's used to establish these plots that I showed of the distribution of energy at different frequency ranges over time. And that's also been quite carefully standardized. Also, an area that Goose has developed, there's a website for ocean best practices, and they're very well established best practice guides for measuring both particle displacement for sound, which has been less standardized, and pressure. I would mention there are many different hydrophones. There are many different ways to measure particle displacement. The key for us is not what system was used, but to have good calibration so that we're confident that the SI units that they should be stored in are correct. And again, there are most developed nations have often associated with the military superb calibration facilities and ways to maintain the chain of calibration, but those are not universally accessible. And if we want biologists and students globally to be able to use systems that now cost very little in a way that's calibrated and useful for this, we need to expand the access to calibration chains globally. It's not a technical problem at all. It's really a question of just willingness to establish a network of collaborators.
Yeah. And then the question by Paula, it's about the data gaps that you mentioned for the Arctic and the Antarctic, and she was wondering whether the very ice sounds that you're interested in measuring will also cause an issue with measuring other soundscapes.
Yes, we have to, the thing about a soundscape, it's dominated by what it's dominated by. So I showed that early hand-drawn figure from the 60s. The reason ocean acousticians wanted to know about how shipping affected the deep ocean ambient or wind and waves did, they were listening for other things. And that this was noise for them. So they just wanted to know how much would it degrade the performance of their system. From the soundscape perspective, I think We just want to know what's contributing to the sound. And breakup of ocean ice does generate a lot of noise, and it can actually be monitored from 1,000 kilometers away.
Mm-hmm.
So this is something where it can be dangerous and difficult to measure close up. And I
Mm-hmm.
think acoustics may be useful for measuring it. But you're absolutely right. If you're interested in tracking whales, you'll do a lot worse during ice breakup than other times of year.
Yeah. And actually, that was a question that I had as well about the information you showed with the ice and the sound, and that looked like it was not really very close to the ice at all.
No.
So you could still use it from that far away. So that's quite
Yeah,
important.
1,000 kilometers is fine,
Yeah.
at least from the Antarctic
Yeah.
areas where there's significant ice breakup.
Yeah. I think Paula's the last bit of a question was the practical aspects of having to deploy hydrophones in those areas. You know.
Oh, I have a great comment on that. So I mentioned that you measure sound from tags.
Yeah.
Uh, this has been less used for sound than for temperature profiles. A key source of global oceanic currents is the temperature distribution in places like the Weddell Sea during the wintertime. And that is a very difficult place for humans to drill into the ice and then be able to measure a full temperature profile.
Mm-hmm.
But Weddell seals make a living by feeding there all year round.
Mm-hmm.
So a group at the Sea Mammal Research Unit in St. Andrews, I'd say 20 years ago, probably started in putting temperature probes on tags on these seals. And they went through an elaborate calibration process with the World Meteorological Association, the organization, in order to make sure that the data had the quality control and quality assurance required. And I think the last number I remember is that 70% of the ocean temperature measurements coming from 70 degrees south and further south came from seals rather than human deployments. So we need to be creative about these things. There will be an animal that will be able to take the sensor to the place you want to make the measurement almost anywhere on the planet.
Yeah.
And luckily, seals haul out on land, so you can get the recorder back.
I remember actually a little side interaction here. I remember I used to work at the University of British Columbia, and they also have a marine mammal unit, and they actually had sensors that they stuck on the seal heads and were trying to find ways to release it. And in the end, they used lifesavers, those little speeds that would dissolve in water. That was the way to release the tag. So yeah, you have to think about how to make these things work.
Yes. Yes. But this is, again, the global community is super helpful, because as soon as somebody anywhere globally comes up with a crazy idea like that and it works, we all take it on board.
Yeah. And again, another question from Astrid is, can you comment on the potential implications of increasing gliders or deep profile Argo flow type measurements with naval military operations? So
yes.
fractions.
So I think that several nations, India, for example, is very concerned about release of any ocean data from their territorial waters. And so Argo, I'm glad that you mentioned Argo. The Argo team, and this is part of what required the global coordination, has a diplomatic process. When an Argo float, which is just floating around, the humans don't control where it goes, when it's nearing a sensitive area, I think that they immediately, send messages to the whatever organization is responsible for the protection of it, and they have a coordinating mechanism to make sure that if the nation really doesn't want measurements to be used, that either they turn off the sensors or have a way to censor the data as it comes out. I think, though, that we live in a world where it's gotten so cheap and so easy to deploy underwater vehicles like gliders or profiling floats, that the navies of the world just have to get used to the fact that the world is going to be full of measurements.
Yeah.
And I think that most nations don't have such extreme views unless there's an active military operation going on.
I'm not sure, because I know under UNCLOS at least, you have to really, if you're going to take measurements in another country's EEZ, you really have to ask permission 6 months in advance. So there's a legal framework, and Argo has been able to somehow circumvent that, but have been able to deal with that through this mechanism that they've established. But it's the only one that they have, and it's probably something that is worth thinking about, especially for something like noise or sound, which propagates so far. So
yes, acoustics is
some problems.
Navies have historically been particularly concerned about acoustic measurements. But I think that and the international trade in arms regulations limit some kinds of systems that, what kind of sensitivity and how deep it goes and things like that. The key is no surprises, I think. I think as the science community develops plans for this kind of work, like Argo, you just need to do your homework to make sure that every jurisdiction knows about what you're doing and has a chance to say what process they want to protect their interests.
Yeah. There's also another question by Christy Hall. She says she's an artist who's looking to work with ocean sound data in her work, and can shared data be accessible by individuals, and how do you go about gaining data as a non-scientist? I think actually, yeah, maybe you'll answer.
Yeah, well, so the individual groups that make the recordings are easy to reach. We don't have there are a couple of things that there's it's a website called Docets about sound in the sea that has examples of shortcuts of sound. You might want things that are a little bit longer than that. The AVI system that I showed processes data, and I think that all that they are storing are those spectrograms that I showed, as opposed to the waveforms, because they're so huge. Actually, if you look at the time series, even a typical university collects in acoustics, it's hundreds of terabytes. Yeah. So the issue of how to archive and make available the raw time series has not really been solved. So I think what you would want to do is think about what species you might be interested in, or what kind of sound, and docets would be helpful to get an idea of those. And then communicating with labs or groups that are making the recordings is, I'm afraid, still the easiest way. The Cornell University has a library of natural sound, and that's searchable. And there's a British library of natural sound that might also be worth exploring.
Yeah. Okay, I don't know if there's any other questions. I'm not seeing any. If not, anything else? No. I think, that was great. I'm not sure. I'm sure I had some more questions in my head, but now they're gone. It's the problem with having a later webinar. It's the end of the day for us. So yes, I guess I started my questions with what's next. What do you think is the most critical thing? You mentioned sort of sustained funding for observations and things like that. Do you think there's something more that, say, the Marine Board can do, or that scientists can do to make that happen?
Yes, I think if individual scientists, particularly ones working in ocean science, speak with their, leaders of their organizations, there's been a culture in ocean science of sharing data, but ocean sound has not fully been integrated into that. And so I just, again, highlight the example of AVI. Several scientists there are deeply engaged in this work, got a commitment from AVI to develop the system. It's a lot can be done on that small scale. For the European Marine Board, thinking about regional networks on an EU scale would be very, very helpful. So the Digital Twin Ocean effort is one that is starting to incorporate sound, but I think that continuing to push for inclusion of sound in those kinds of ocean observation networks, and making sure that it coordinates with the global
Yeah, yeah,
system is great because the standardization is available, but most labs start doing their own thing.
yeah.
Most regions often do their own thing.
Yeah, at least in Europe, I would say the most obvious place for those kind of um, to be able to get access to all of this data in conjunction with all the others is EMODnet, which basically will give you access to, or at least tell you where to find access to really all the data. So I'm hoping, assuming that the RV data is actually incorporated into the EMODnet human impact, I would imagine would be the well, I'm not sure because it could also just be biological data. So that's a good question, and maybe we should speak to our EMONet colleagues about that.
Yes, it's one of the tricky things is the ocean sound is just a physical measurement,
Yeah,
but with the derived data products, they're primarily important for interpreting biology.
yeah,
Yeah, so it's interesting that way, and
yeah,
sometimes it slips through the cracks.
yeah, and so yeah, it might even be part of EMONet physics, but the other part of it is actually under the digital twin of the ocean. I think there's a lot of work that could be done by the sound scientists in Europe to be part of the digital twin of the ocean model lab, because it seems to me that it would be an easy one to show proof of concept for doing this. And if they already, at least the physical parameters you should be able to get that anyway. So I think that would be a good one. Yeah.
Yes, I'm part of a project funded by Horizon 2020 that is looking at detections of harbor porpoises in the North Sea. And they're fantastic species for measuring the density and abundance acoustically, because scarcely a minute goes by without each porpoise making these clicks. So
Yeah.
you don't need to worry as much about the rates at which they're calling. And there have been a bunch of automated detectors have been put in place so that all we need to do is store detection data.
Yeah.
And everybody's pretty comfortable with the data flows of the time and the location and detection data going into EMODnet. When you mention acoustic data, eyes glaze over. And porpoises, their clicks are 130 kilohertz. So you need to be sampling at a million bytes per second in
Yeah.
order to detect them. So the actual raw data files are enormous.
Yeah.
And
But
maybe we just need to stick to the detections, but I actually feel that long term,
yeah.
the goal is going to have to be managing the physical data is in terms of SI units is so much easier.
Yeah.
It's just that it's a large this volume of data
Yeah.
overwhelms what we've been as
But
biologists used to.
maybe it does need to be processed into something that's actually more manageable. And that's, I guess, from a carbon guilt perspective, storing data is an expensive thing. So maybe that's something that your community needs to think about. How can we turn these huge things of data into something that's more storable?
Yes. So the kind of approach we've been thinking of is just snippets. You get a variety of detectors of the things you're interested in, and then store waveforms of, say, detect a sample of the detections and a sample of the no detection data. But it the actual end the end product of the detections, you always have a lot of misses and a lot of false detections. So the QA/QC is very complex.
Yeah. Yeah.
Yeah.
All right. I think we're nearly at the end. So I think there's only time left for me to say thank you so very much again, Peter. That was great. It was really interesting to hear what you guys are doing, and to know that actually, the work that we've done is also very much linked up with that. And to mention that our next webinar will be on Thursday, the 21st of March. No, that's today. That must be then Thursday sometime in April. And the question, the speaker will be Nikki Beaumont, and the question, the title of her talk will be the why, what, how, and how of interdisciplinary endeavor. So it's very much something completely different. We will let you know the time and date of that talk in due course, I think. So maybe somebody can tell us in the chat quickly. But thank you very much, Peter. It was great to have this conversation, and yeah, we look forward to hearing from you again.
My pleasure.
Thanks. Bye.
Bye.